Hello and welcome to the TTI Distribution Download, the podcast where we talk about all things happening in the world of electronic components with the specialists of TTI. And now, your host for the TTI Distribution Download, Paula Renfrow.
Thanks, Jim, and hey, everybody. Thanks for plugging in today to the TTI Distribution Download in our second episode with our partners from YAGEO. In this series, we're discussing very hot topic, artificial intelligence. Joining us again today is Dr. Philip Lessner. Welcome back.
Thank you, Paula,
for hanging in here with us. Today we're going to talk about how AI is impacting our industry and how is it impacting electronics. And joining us is Peter Blais, Senior Director of Application Engineering at YAGEO. Welcome, Peter.
Oh, thank you, Paula.
As we get started today, tell us a little bit about your journey.
Oh, my journey. Well, my journey within YAGEO started about 20 years ago when I joined Chem Electronics Corporation, and I've been basically involved with applications engineering within the organization that entire time, expanding my role. Currently, I manage the team of applications engineers here in the Americas, and then I also have responsibility for our technical marketing organization, which is really delivering the tools and the content necessary for design engineers to do their work easier, simpler, and more efficiently.
Cool. Thanks again for being here. So today, as we kick off our episode on how does AI impact electronics, let me ask you this specifically. What are the biggest challenges for AI in electronic systems?
So in the last episode, we heard Dr. Phil explain that originally artificial intelligence really didn't get traction because we didn't have the computational horsepower to go and run all of the algorithms. And today, we do have that computational horsepower in the silicon. And what we're observing is the semiconductor companies are making some drastic leaps forward with the semiconductor technology, increasing the gate count within the processors. And what this does is, if you think about the processors, you've got a massive number of transistors that are switching to do the computations. And this all takes electrons. So as we increase the number of transistors in the computational processors behind AI, that is creating the need for ever-increasing level of flow of electrons into them. Or, in other words, we're increasing the power consumption needed for the electronics of AI and the processors. When we look at the roadmap of the semiconductor companies, we're seeing next generation processors that are going to be in the order of roughly half a magnitude larger in scale for power consumption. And this will place a significant strain on the subsystem within the electronics, which powers the processing semiconductors or the computational semiconductors. Looking at this network, or we refer to it as the power delivery network, what's going to happen is we need to go and develop systems that are more efficient and also more compact in size to go and be able to place in the available space to power the semiconductor. The other issue is when we take a look at these processors, they can have two states. They can have the active state where they're consuming maximum power, and they can also have an idle state when they take a little bit of a pause. During that situation, the number of electrons that they're consuming can drastically shift from, if you take a look, think of an analogy, think of the amount of water flowing over Niagara Falls, massive amount, and then the next moment, you get a little drip out of your tap faucet that's leaky. So you need to be able to manage this drastic change in flow of electrons in the power delivery network as well, and that's what we call as load transit. And this also places significant challenges on the PDN.
Should we talk a little bit more about power density and efficiency?
Absolutely. So one of the challenges is as these processors are consuming more power, the power delivery network needs to surround them, and the allocated space to do this is reduced. Also, because of the increase in spread or breadth of load transient, you need to be able to react faster and absorb the energy or deliver the energy in momentary shifts of variation in power consumption. So the PDN architects, they're doing a few things. Number one is they are increasing the number of phases in the PDN This allows for a more rapid response to load transient. The second thing is that they need to come up with new geometries for these systems, also incorporating some interesting packaging techniques such as embedding some of the semiconductors into the system to reduce volume and footprint. The other thing also is that they must select components with new materials and also new geometries of materials, of components with these new materials, in order to go and lower the parasitic losses. Parasitic losses within the components, really all that does is take the energy flowing through them and convert it to waste heat. And we don't want to be converting energy to waste heat because that's going to create thermal issues for the entire system. So when we take a look at the PDNs, really two things are happening. Number one is they have to come up with new architectures of the systems, new geometries of the components going into the systems, and there's new material sets going into the components of those systems to lower the parasitics. And this is whether it's magnetic materials or capacitor materials, all of these are being incorporated.
So when we talk about power density and thermal issues, what does this do to reliability?
So the thermal issues, first issue is, number one is you want to reduce the creation of heat, because if heat is being generated, you've got to be able to pull it out of the system somehow. Existing systems today are generally doing this through forced air cooling, where you're blowing air-conditioned air over the components to help them dissipate the heat.
So this is increased design challenge to the design engineer.
Absolutely.
Got it.
So that only gets you so far. And then as we take these systems and make them more dense, the power density is increasing, the waste heat being generated is increasing, and it's creating more challenges to go pull the heat out. And so one of the things that they're doing is they're looking at what we call immersion cooling, where we're actually putting the electronics in a liquid, and there's more thermal conductivity between the components in the liquid than components in air. It's a much more efficient way of pulling the heat out of the system. So that's one of the things that's occurring related to thermal issues, to be able to improve whatever waste heat is generated to pull it out of the system. And it's critical to deal with thermal issues. And the reason is when we look at these systems, they tend to be designed to operate 24/7, 365 days a year, and upwards of 7 years, which is a long time, and it's really taxing on the components. So you need to design the components so that they survive a longer period than the mission profile that they're being placed into. One of the key parameters that's putting stress on the components is temperature. So if you're not managing the thermal conditions that the components are being exposed to properly, you're going to prematurely wear them out. And a good analogy is, I like to use this with when I talk to people and why it's so important that components last. If you go to an ATM and you want to withdraw money out of your bank account, all of this data is stored in servers in the cloud somewhere. No different than in AI, all of the data that's being processed and churned and evaluated to come up with new patterns, that's all being stored. Well, when you go and withdraw your money from your bank account, you don't want there to be a momentary glitch or failure somewhere in some component and the machine reads, account not found. That would elicit a rather negative
heart attack.
that would elicit a very negative reaction from the bank account holder. So reliability is very important. You cannot have components failing or systems failing during critical operations. And when we look at AI, when we're training the systems, to train an algorithm, whether it be for autonomous driving or whether it would be for coming up with a new strategy for winning a sports game or something, that whole process of training may take months, because it's an iterative process and it keeps on learning from the previous exercise that it did. And you don't want the hardware to fail mid-training exercise because, oops, all of that work is just thrown out the window, and then you have to start all over. And these systems are extremely expensive.
And is this why capacity, you mentioned earlier, is also so important?
So capacity is important because if you take a look at the companies that are developing the hardware, They are developing a new architecture that's going to have more capability than the previous platforms that are out there. And their engineering teams are going to spend a lot of time developing a new approach or new PDN architecture, new silicon architecture. When it's launched, the consumers, their customers for these big data centers or the big AI centers that are consuming their products, they want to ramp up and they want to go and execute on this new capability. And so the supply chain, whether it's YAGEO Group or the semiconductor guys that are supplying the PMICs, whoever it may be, they need to be able to go and scale up in literally a matter of months to maybe a year in order to go and meet the demands of these new data centers that are being put into place. So you need to have a supply chain that really has the financial strength to go and scale up capacity, especially if it's really surrounding new materials, right? So if it's an extension of an existing product, really easy to scale. But if it's a new material set, or a whole new geometry which requires a retooling of an existing production line, you need to be able to turn that on very quickly and support the demands of the volume production because it kicks in real fast.
So is the design cycle time, the engineering design cycle time with AI changing?
So that's a really good question. I do believe it's changing, and I do believe it's accelerating. It's going faster. And when we take a look at design cycle time is nothing new. I mean, if we took a look at, we alluded to the internet and the creation of the internet and the cloud and all that stuff in the earlier podcast. There was design cycle times and technical innovations occurring all throughout that entire process. And then AI is really just an extension or an evolution of what's already taken place. The pace, though, of innovation is increasing, and the design cycle time is also reducing. In other words, you've got more innovation occurring in a much shorter period of time. And so the way I look at it is, this is really almost like an arms race, but it's an arms race between the ecosystem that supports AI and the different suppliers within that ecosystem. I always like to take a look at the graphics chip companies, from back in the 80s. I was around at the dawn of the PC industry, and, so I observed it firsthand. And originally there were roughly, say a dozen semiconductor companies that were producing graphics chips. They were dotted all over the place. And, everybody had their features that they promoted to the PC companies. And it was really interesting because, every few years, one of them would have a feature set that was significantly more advanced than the remaining players in the graphics chips companies. And they would gain a lot of design sockets within the PC industry. And then it's like, the company, they would pound their chest to see how great they were, and they just would decide, we need to build a new headquarters because we need to be able to support all of our new growing graphics chip business. So they would build a new headquarters, and everybody's focus was on the architecture of the new headquarters and the style of the lobby and this stuff and that stuff. And something amazing would happen. The other players in the graphics chip industry, they were still kind of mad that they didn't win all of these sockets. And so they would work really hard to go and increase the feature set of the next generation graphics chip. And lo and behold, when the PC industry would go and do a new generation of PCs, this company that just was building their brand new headquarters, because they weren't focused on the graphics chips design, they were focused on the aesthetic waterfall in the lobby of the headquarters, they would lose out on the sockets. And within a couple of years, they kind of go by the wayside. This occurred year after year in the PC industry. And really, we ended up with going from a dozen graphics chip companies to about 2. One of them is NVIDIA. The other one was ATI, which was a number of years ago absorbed or acquired by AMD. The joke in the industry was, so-and-so company is going to go out of business because they built a new headquarters. In the case of AI, the same thing, it's an arms race. Everybody is trying to beat everybody else. And the interesting thing about my graphics chip story is if we take a look at the companies that are really powering the processors behind AI today, the top guy is NVIDIA, and AMD, which is the former ATI, graphics chip company. They are the, up and coming number 2. So, and there's a number of other players out there that are trying to get into the space as well, and companies designing their own silicon. But yes, it's design cycle time, if anything, is compressing, and the complexity of the changes from generation 1 to generation 2, the complexity per iteration is also increasing drastically.
Great explanation. Thank you for that. So how do these challenges affect the design and development of components? And Dr. Lessner, would you like to take that one?
Sure. So Peter touched on one of the really important factors, and that's the parasitic losses in the components. So those are losses like equivalent series resistance, or ESR, equivalent series inductance, or ESL, core loss in inductors. So they have a great impact on our development going forward, because that's one of the key areas that we're trying to address, and that really addresses both the stability of the power network and also the thermal losses in the components, and therefore the temperature rise in the system. So a lot of our material and product development effort is going into decreasing those parasitic losses. Another area that Peter touched on was that these servers are getting so hot that they're considering the move from air cooling to immersion cooling in various liquids. So there's a lot of questions out there right now about the compatibility of different component families with these immersion cooling liquids. So we're putting a lot of effort into understanding the compatibility of our different component families with immersion cooling. And then I think the final area that, really focusing on is reliability. So to follow up on one of Peter's comments, these training runs for the servers, for the AI and the servers, they take a long time. They could take anywhere from days to weeks and cost hundreds of thousands to millions of dollars. So if there's a failure in the midst of one of these training runs, that's a lot of wasted time and potentially a big wasted monetary value. So we're working on increasing the reliability of components by increasing the temperature rating, increasing the lifetime, and we shouldn't also ignore that some of these AI applications will be at the edge, so they'll be in autonomous vehicles, or they'll be in IoT systems that are deployed in the field. So another aspect of reliability is hardening the components against humidity exposure and other environmental factors.
Wow. So on this topic of immersion cooling, is this a new competency that our design engineer is going to be faced with, or is this going to introduce a new personality, a scientist, a chemist into our world?
Well, definitely it requires chemistry knowledge, and the YAGEO group has excellent facilities for doing chemical and microscopy analysis. So out of our facility in the U.S. in Simpsonville, South Carolina, we're leading the effort to study the compatibility of these components with these new immersion liquids.
Very cool. Okay, so speaking of, in our next session, we're going to talk a little bit more about the components specifically, right? We're going to welcome back Mark Lapps. And Peter, thank you very much for joining us today.
My pleasure.
It was fascinating. Also in our next episode, we're going to introduce you to E2DI, which is YAGEO's philosophy on producing products that are easy to design in. In the meantime, I encourage you to stop by tti.com/marketeye to read Dr. Lessner's article, Advancing Artificial Intelligence, YAGEO's Role in Powering the AI Revolution.
That's it for this episode of the TTI Distribution Download. For more information on any of the topics you heard about today, reach out to your nearby TTI branch at 1-800-CALL-TTI or visit us online at tti.com.